Welcome to physics for November the 9th. And I'm also going to use this recording for November the 10th for the B-Day class. Before we get into the homework and the new material, let's talk briefly about a few important announcements. One is, don't forget about the test rework that's due this coming Saturday at midnight. And you have to redo all problems, not just the ones you missed, but you got to do them all. Also, remember that the Zoom study groups are forming up, and there's a link on Canvas. I put a link on there to a Google Doc that Lila is running, where people can put their emails and connect up with other people who want to get in a Zoom study group. I really highly encourage you to do that. I think it'll help a lot. Now, just FYI, I am trying to get Mr. Wilson to approve me to have some of the U of U physics students work as paid tutors, so that if you're having trouble forming a study group, which I understand some of you are, that I will have these U of U students, they will host study sessions on a regular basis, and they know physics really, really well, and they would be wonderful to help you. So fingers crossed we can get that done soon. I can't promise it, but it looks hopeful at the moment. Also, last Friday morning, I was here on Zoom from 9 until 10:30. I was disappointed with how few people showed up. If you guys don't take advantage of these study sessions, we may not be able to continue doing them. So you need to show up and take advantage. The people that were there, it sounded like they learned some good stuff. Also, this coming Friday, I will not be able to do a Zoom study session because I do have a U of U physics class meeting, and I need to be with them. So I'm really hoping that we can get these paid tutors going quickly, but I can't guarantee that. And then last, don't forget about Engineering Day, November the 21st. That's coming up quickly. Very cool experience, and I will give extra credit for it. So, hey, can't beat that. All right. Any questions before we talk about last night's homework? Not seeing any, not hearing any. Okay, then here are the answers to the ones that you haven't already looked up. And you'll see that there's a couple here that I want to discuss. But before we do that, let's see what ones you want to discuss. So let's do the same thing we've done before. It's very unlikely that we'll be able to do very many of these problems. We might only have time to do one or two, depending on which ones you choose. So everybody, please type into the chat box. Let's vote. If you could only see one problem worked through, what would you want that one problem to be? Okay. All right, I'm seeing 17 a couple times. That is definitely one that I had intended to talk about. 18, 17, 18, not 65. I'm surprised. The other class, they overwhelmingly voted for 65. You guys good on 65? Okay. All right, 17 or 18 looks like it's kind of a tie. So I think we can do both of them. Let's see what we got here. So on 17, okay, so you're in the back seat of a car going around a curve to the right. So we want the free body diagrams and the motion diagrams. Okay, so here I find that it's very helpful to draw two pictures from two different points of view. Let me open up a whiteboard. Okay, so one point of view is, let's assume that you're in a helicopter up above looking down. So here's the curve, and here's the car. And so if we draw the velocity vector in blue, okay, there's your velocity vector. And then later the car is over here and the velocity vector is over here. So that's V final, and this is V initial. Okay, and so that gives us some insight as to what's happening. But, and this is the top view from a helicopter above looking down. But I also find that it's very helpful if you draw a view, assuming that you're in a car following behind the car that you're interested in doing the free body diagram on. Okay, so imagine you're in a car behind looking at the car in front of you. So here's the car, here's the wheels, here's the road. All right, and so the car in front of us, that's the car that we want to do the free body diagram on. So let's do a free body diagram. Let me switch to a different color and make my pen fat. All right, so we've got mg going down. We've got the normal force going up. Now, if the car is located over here, so the car is turning to the right, well, there must be a force that's causing it to turn to the right. And so there, that would be the force. And what is the nature of that force? Now, some of you are going to say it's a centripetal force. And I mean, you are correct in saying it is a centripetal force because that force will be pointed toward the center of the circle. And when the car is over here, it'll be, so wherever the car is at any time, that force is always pointed toward the center, which is what centripetal means, but that doesn't tell us what the nature of the force is. So the nature of the force is the friction between the tires and the road. So I'm going to call that force of friction. And on this picture here, I'm going to label it force of friction. Now on the top-down picture, you can't really show the mg force and the normal force. You can really only show the friction force. That's why it's good to have both pictures going at the same time. Helps you to understand better about what's going on. Okay, so question A, what's the direction of your acceleration? Well, the direction of the acceleration is the same as direction of the force. So if we draw the acceleration vector in a different color, okay, it's always going to be pointing toward the center, no matter where you are. The force is pointing toward the center and the acceleration is going to be the same way as the force. Okay, so that's the direction of the acceleration. The direction of the net force, well, okay, we've already answered that. What is it that exerts the force? Friction. Don't say it's centripetal. That doesn't answer the question. That only answers, that only tells you what direction it's pointing. The nature of the force is friction. Okay, and, oh, wait a minute, that was 17 that we did, right? Okay, so now let's do 18. Okay, so we've got a string whirled horizontally, or a stone whirled horizontally. We want to know the tension of the spring. Okay, now here, this, if we solve this problem right, it's actually a kind of a complicated problem. And by the way, when we do our homework problems tonight, you're going to find out that I have a problem very, very similar to this in the homework problem tonight. But you can make some simplifying assumptions sometimes. All right, so let's look at this. Let me open up a new picture here. Okay. All right, so what you're seeing right now, oops, that wasn't what I wanted. Why did it do that? Okay, what you're seeing right now, at least up at the top, that's the way that they want you to analyze this situation. They want you to assume that the thing is going so fast that the string is basically horizontal. Okay, basically horizontal. Now, I'm hoping that you guys realize that that can't actually be the case. It's impossible to have that string really truly be horizontal, because if we were to do a free body diagram on this thing, okay, so we're going to have mg going down, and the only other force that's acting on the mass is the tension of the string. It is impossible for the tension of the string to work out to match the downward force of the mg, because mg is pulling vertically downward. If the tension pulls perfectly horizontal, That's an impossible situation because that ball is going to move downward. Okay, so what you see here is the more real case of what's actually going to happen. The ball is actually going to sag down a little bit. The ball is actually going to sag down a little bit. And so let's look at this exaggerated picture here because it's easier to see. So you're going to have mg going down. And the tension has to have somewhat of an upward component because something has to counter that mg going down. And so the tension actually has to be like this. And so we're going to have two components here. We're going to have T cosine theta here and T sine theta here. You have to have something to counter the mg going down. That's a G, not an A. Okay. But if you swing that thing fast enough, then what happens is you have a picture that looks more like this. So here's the hand, here's the string. And so if you break it up into its components, okay, so here you have mg going down, and the T cosine theta component is so small because if the thing is swinging so fast, then this angle here can be a number that's really, really close to 90 degrees, right? So this angle here could be like 89 degrees, leaving this angle here as 1. And so if that's the case, then the tension force is not exactly horizontal, but it's close enough to horizontal that if you just assume that it's horizontal, then it makes the math easy to do. And you get an answer that's really close to the right answer as long as this angle right here is small. So in problem number 18, we're going to make that assumption. But in tonight's homework, we're not going to make that assumption. In tonight's homework, we're going to do it the right way. Okay. All right. But for now, for problem number 18, we'll just go ahead with this simplified assumption. We will assume that this thing is so close to horizontal that we can treat it as horizontal. So we get the mass is 40 grams, which is not a standard physics unit. So we have to say 0.040 kilograms. Okay, the length of the string is 0.6 meters. And the speed is 2.2 meters per second. Okay, so we want to know what the tension in the string is. Well, if you make the simplifying assumption that we've just talked about, okay, then here, let me clear these guys out. Okay, so what we're going to do is we're going to assume that we don't need to worry about this. And so then if we look at the force here, the tension force is acting that way. So let me get rid of, okay, so the only force in the is in the x direction, which is the tension force. And so then when we do sigma F equals MA, then tension is the only force we need to deal with. Now, in reality, it's a little more complicated than that, as you'll find out in tonight's homework. But for right now, we're going to assume that it's that simple. Okay, and then that's mass times acceleration. Now, what is the acceleration? Well, this weight on the end of the string there is moving at a constant speed. But hopefully you guys now understand that that doesn't mean that it's not accelerating, because if the direction is changing, it's accelerating. Even though the magnitude of the velocity isn't changing, the direction of the velocity is changing, it is accelerating. And so what is the acceleration then? Well, that's the centripetal acceleration, which is v squared over r. Okay, so from this point on, it becomes really, really easy. We know what the mass is. We know what the magnitude of the velocity vector is, and we know what the radius of the circle is. So we plug it in and bingo, we get the answer that you saw on the other sheet there, which was, oh, okay, let's go. Okay, up here, okay. Now in tonight's homework, we will do it the more correct way. And we'll find out how much of an error we made by doing this simplification. Okay, Any questions about that? So type yes if you think it's good to move on to the next one, next new material, and if you have a question, go ahead and type in your question. All right, looks like I'm seeing lots of yeses. Okay. All right, so 17 was one I wanted to discuss. We've already done that. Another one I want to discuss is number 19. So let's talk about number 19 here. So what it says is you've got a newspaper article talking about that when you're going around a corner, you want to balance the centripetal force and the centrifugal force. Okay, so last time we met, we said that the centrifugal force isn't real. And so they want you to write a letter explaining that. So I'm not going to have you write a letter, actually. But I do want to make sure that everybody fully understands that centrifugal force is not a real force. If you look at it from the outside, if you're the outside person looking in, it's not a real force. But things get interesting if you change your point of view. And the best way to explain that, I think, is with this little cartoon that I have here. I don't know if any of you guys are familiar with the cartoon series called XKCD. It's a cartoon series that's basically for nerds, which means I love it, as do a whole lot of other AIM students. Okay, so what you see here is James Bond is strapped to a machine called a centrifuge. It's something that spins really, really fast. And so the guy at the controls there, that's Dr. Evil. All right, so let's read the thing here. It says, "How do you like my centrifuge, Mr. Bond? When I throw this lever, you will feel centrifugal force crush every bone in your body." Now, James Bond responds to that by saying, "You mean centripetal force? There's no such thing as centrifugal force." Dr. Evil responds by saying, "A laughable claim, Mr. Bond, perpetrated by overzealous teachers of science. Simply construct Newton's laws in a rotating system, and you will see a centrifugal force term appear as plain as day." Now, I'm willing to bet that what Dr. Evil said here probably leaves most of you saying, "Huh? What is he talking about?" Well, you're going to find out real soon. But for right now, let's just go with the fact that James Bond is saying there's no such thing as centrifugal force. So is that going to save his life? Okay, so let's see what happens. So when Dr. Evil says that there really is a centrifugal force if you just construct Newton's laws in a rotating system, so James Bond replies by saying, "Come now, do you really expect me to do coordinate substitution in my head while strapped to a centrifuge?" To which Dr. Evil says, "No, Mr. Bond, I expect you to die." Okay, so now I propose the question to you guys. Is James Bond going to die? When Dr. Evil turns on the power to his centrifuge and starts spinning really, really fast, is James Bond going to get crushed? What do you think? Anybody want to unmute yourself and tell me? How about Aurora? What do you think, Aurora? Is James Bond going to die? I'm sorry. That's a good one, Aurora. For those of you who are watching the recording, Aurora's response was, "It depends on how long ago he ate." I can't argue with that. How about Austin? What do you think? Is James Bond going to die?
I mean, I feel like probably because I mean, even if it's not a real force, it's still gonna like squish him. But I feel like you'd have to go really fast to do that.
Oh, yeah. Yeah, you'd have to go really fast. But yeah, if you could go fast enough, James Bond would get crushed. Well, now, admittedly, I mean, James Bond is James Bond. He'll probably find some way to escape. Okay. But if it was you and me, okay, if it was anybody other than James Bond, they would get crushed. Now, what is it that crushes them? If there isn't really any such thing as centrifugal force, then what is it that's crushing them? So let's see, Amy, what do you think it is that's going to crush the person here? Okay. Okay, she's not sure. She likes the question, says it's a good question. How about Cindy? What do you think? What is it that,
A type of force.
so what is it that crushes him? Okay, all right. So I tell you what, I'll go ahead and answer the question. All right, so let's draw the velocity vector for James Bond when he's in the position that you see right here. So here's James Bond, and if the thing is spinning this way, then at this instant right here, James Bond is moving that direction. And later on, when James is up here, he's moving that direction. But let's focus in on this right here. So remember Newton's first law, the more complete version? It says an object in motion wants to remain in motion in a straight line. Okay, so James Bond's body is right here. So, and it's moving this way. So it wants to keep in a straight line. It wants to keep moving that way. And the faster it's going, the more it wants to keep moving. It's got lots of inertia. But the centrifuge is not allowing him to do that. And the centrifuge is exerting a force on him, pushing toward the center of the circle, which is correctly called centripetal force, not centrifugal force with an F, but centripetal with a P, okay? And so what's happening is you've got the centripetal force going, pushing one way, and then you've got your inertia pushing the other way. So the thing that crushes Mr. Bond is inertia doing what inertia does. And the faster he's going, the more inertia he's got. And so that's what's going to crush him is his inertia. Okay. Now, let's go back and let's talk about this thing that Dr. Evil says here about, he says that if you construct Newton's laws in a rotating system, then there will be a force that's centrifugal force. Okay, so here's the thing. Remember how I have said many, many, many times that you can choose your origin anywhere you want your origin to be. If you're doing a problem where you're shooting a cannon off the top of some tower and you call in the good twin and you have the good twin help you out, okay, you can put your origin at the bottom, you can put your origin at the top. Hey, if you wanted to, you could put your origin somewhere in between. Okay? And you will get the same answer no matter what. Well, it turns out you can also have a moving origin. And so you can have an origin, you can make it so that James Bond is the origin, and it's a moving origin. And boy, does life get interesting when you do that. Now, a good way to illustrate that, I think, is if I were to share a movie with you. How many of you have seen the movie 2001 Space Odyssey? You know, raise your hand or give me a thumbs up or something if you've seen the movie 2001 Space Odyssey. Okay, I see several of you have. Good. In my opinion, it's one of the best movies ever made. Okay, so I'm going to show you a scene from that movie. And those of you that have seen the movie, we're in the spaceship. We're traveling to Jupiter. And they have artificial gravity, which is something a lot of science fiction movies, they have artificial gravity, but they never explain how they do it. It's just some magic thing. They flip a switch and somehow magically they have artificial gravity. But in the movie 2001 Space Odyssey, it's not magic. You see how they do it. Okay, so let me just show you a very brief clip from the movie here. So that man that you're seeing right now is one of the astronauts, and he is jogging on the walls of the spaceship. Okay, so you see Now that thing he's doing with his arms is just, to give him a full body workout here. But he is jogging on the walls of the spaceship. He's feeling something that to him feels exactly like Earth gravity, but he's in outer space. So how is it possible that this astronaut in outer space can feel something that's exactly like Earth's gravity? And how is it possible that he can jog on the walls of the spaceship? Okay. So Calvin is suggesting because the room is rotating, and Calvin is exactly right. So what's happening is basically the same thing as when we had James Bond in the centrifuge. So let's go back to this one because it's a little bit easier to see. Okay. So let's assume that the centrifuge is the spaceship, and our jogger is right here. Okay. And so the centrifuge is spinning. And so what this jogger is going to feel is inertia, just the same as what James Bond is going to feel, although hopefully to a lesser extent, so that we don't want the jogger to get crushed like James Bond does. But if this thing spins at the right speed, then the inertia of the jogger's body will give him a force which he might be tempted to call centrifugal force. Okay, because think of it this way: if the jogger had been born and raised inside the spaceship, so that the jogger had spent his entire life inside the spaceship, and let's assume that it's a spaceship that doesn't have windows, so he doesn't know that it's spinning. He has no way of knowing that it's spinning. All he knows is that when he is located right here, he feels a force that pushes him toward the wall. When he's located over here, he feels a force that way. When he's located over here, he feels a force pushing him that way. So he feels something that it feels exactly like gravity. From his perspective, it is a real force. Now, somebody on the outside looking in recognizes that it's not really a force, it's really just inertia doing what inertia does. But if you change your frame of reference, if you change your origin, so that instead of being an outsider looking in, if you put yourself in the position of the astronaut who was born and raised inside this rotating frame of reference, then he feels a force. And as far as he's concerned, it's every bit as real as the gravity force that we feel. And so for that perspective, maybe Dr. Evil is not wrong. Maybe that if you choose your coordinate system to be a rotating coordinate system, then centrifugal force is a real force as far as you're concerned. Okay, so that's the reason why centrifugal force is so common. Well, it's such a commonly used term. Okay, now while we've got the picture in front of us here, let me ask a problem like you might see on a test someday, wink, wink, nudge, nudge, or like you might see in your homework tonight. I would like to know, how fast does the spaceship need to rotate in order for the jogger inside it to feel a centrifugal force that is the same as if he was on Earth? Okay, so this is a problem like you might see in your homework tonight. Now, in order to do the problem, you're going to have to know one important piece of information. You're going to need to know what is the radius of the spaceship. So basically, so this distance from here to here, call that D. Okay, so you're going to need to know what that distance is. So most people are about 1.5 meters tall. So this is about 2 from here, from the floor to the ceiling is about 2 people. So let's call it 3 meters. Let's say that, and let's not call it D because then that would be confusing. People would think it was the diameter. Let's call it R. So the radius of this spaceship is 3 meters. So I propose to you that you could calculate what does the velocity need to be. Okay, so if we pick some point here and we say that point, that speed is moving at some velocity v, and the magnitude of that velocity, which we'll just call v without an arrow on it, that's what we want to know in order for the jogger to feel Earth-like gravity. Okay, could you guys do that? Now, ideally, what I would do is I would pause right now and I would let you guys chew on it for a while and see what you come up with. But we are kind of short on time. We got a lot of stuff we need to do. So I'll work through it for you. But ideally, you guys should do this yourself. Okay, so what we want is we want to know what is the force. And so what we're going to do is we're going to say sigma F equals MA. Okay, so now, if we work with a rotating coordinate system, it gets really confusing. So let's put ourselves on the outside looking in. So let's agree then that because we're outsiders looking in, there is no centrifugal force. And so what is happening is the floor is pushing up on the jogger. And so that is the centripetal force, not the centrifugal force, it's the centripetal force, okay? And that's the only force that's acting on the jogger. All right, so the centripetal force is equal to the mass times the acceleration. Now, what is the acceleration of an object that's moving in at constant speed in a circle? It's v squared over r. Now, the centrifugal force, well, that is equal to mass times acceleration, okay? And so you can see the acceleration, we want the centripetal force to be the same as gravity. So this acceleration here, let's put that in as little g. We want the centripetal force to be the same as if he was on Earth. We want that to be mg. So what we've got then is mg equals mv squared over r, and the m's cancel out. So then we multiply both sides by r and take the square root. So then the velocity that we need is the square root of r times the g that we want him to experience. We want him we want his centripetal acceleration to be the same as what his acceleration due to gravity would be on Earth. Okay, so now all we have to do is put in the numbers there. So the square root of the radius, which we decided was 3. Okay, so square root of 3 times the acceleration that we want him to experience, which we want to be the same as Earth, so 9.8. Okay, so that tells me that the velocity needs to be 5.4 meters per second. That's how fast some point on the rim of the spaceship needs to be moving in order for the astronaut inside that spaceship to be experiencing artificial gravity that is identical to Earth's gravity. Okay, so what do you think? That makes sense? Okay. All right. So let's go ahead and talk about tonight's homework. Now, my plan for tonight is not to give you any new physics. I'm just going to take the same physics that you've already learned and just apply it using situations that are a little bit more complicated. So the mathematics is going to be a little harder, but the physics is really the same physics. Remember a while back, I told you guys, my number one goal for you is not for you to learn physics. Now, obviously, I do want you to learn physics, but it's not my number one goal. My number one goal is for you guys to be good problem solvers. I want you guys to be skilled at solving difficult problems. So tonight, the problems that I'm going to give you are similar to the ones that you did last night, but we're gonna approach them a little bit. Well, like for instance, the problem that we talked about with the ball on the string, where we made a simplifying assumption. Well, tonight we're not going to make that simplifying assumption. Tonight we're going to solve it the right way. All right. So, and then there will be other problems like that, where tonight we're going to solve a little bit more interesting ones. So let's go ahead and just jump right into it. Okay, so this problem. So a few minutes ago, we solved this problem, but we did it by making the simplifying assumption that the string in between the guy's hand and the weight, we assumed that that was perfectly horizontal. So basically, we were assuming that that angle there was a number that was so close to 90 degrees that it might as well be 90 degrees, okay? But now tonight we recognize that that's not the case, because this thing cannot actually be horizontal. Yeah, I mean, it can be close, but it cannot actually be horizontal. It has to hang down a little bit. All right, so let's do a problem like, let's suppose that I tell you what the angle is that it's hanging down at. Okay, so I tell you what theta is. Let's suppose that I say theta is some number that's close to 90. Let's say it's 85 degrees. So it's close to 90, but not exactly 90. All right. And it might be helpful if I tell you what the mass of the ball is. So I don't know, let's just make up a number here. Let's say the mass of the ball is 0.1 kilogram. Okay, I don't want it to be too strong. When you're swinging something over your head like that, you don't want it to be too heavy of a thing. You might knock yourself out. Okay. All right. So I want to know how fast is this ball moving if the angle is 85 degrees. Okay. All right. So let's see how we would go about solving this problem. So first thing, free body diagram. Right, what do we got? We got mg going down. We got tension going that way. And let me get rid of this thing. Just, whoops. Okay. So those are the only forces that we have acting on the object. Now, one of them is a funky force, tension. So let's break it up into its components. So we've got a horizontal and vertical component. So if this angle here is theta, hopefully you guys agree this angle down here is also theta. So then if the hypotenuse is t, then this side here is going to be t times the cosine of theta. That's a terrible cosine. Let's see if I can write that a little bit better. T times the cosine theta. This guy right here is going to be t times the sine of theta. Okay, so now that we've got them, we don't need t anymore, because we can replace that funky force with his non-funky components. All right, now that we got our free body diagram, now let's apply Newton's second law. So sigma F in the x direction equals mass times acceleration in the x direction. And if we look in the y direction, we have sigma F in the y direction has to equal the mass times the acceleration in the y direction. So remember the strategy that we learned a while back is when you have two-dimensional things going on, you break it up into horizontal components and vertical components. All right, so now in the x direction, well, that's the direction the ball is moving. Okay, the ball is moving in a horizontal circle and it's moving at constant speed. So the acceleration then is mv squared over r. So I see in the comments, I see that I froze up a little while there, apparently. Am I still frozen or am I back good now? I'm good now? Okay, good. All right. So what we're doing is we're breaking things up into horizontal equations and vertical equations, kind of like the good twin, evil twin thing, right? All right, so in the x direction, I only see one force. I see that force right there. So then in the x direction, my only force is t times the sine of theta. And that's equal to mass times the acceleration in the x direction. And so we're moving in a horizontal circle, and we're moving with what's called uniform circular motion. That means we're going in constant speed, but our direction is changing. So the acceleration then is v squared over r. All right, so we have an equation, and it relates the different variables here, but we got multiple variables in there, and so we're going to need to have at least one more equation. Where can we get the other equation? Well, look in the y direction. So in the y direction here, let's figure out what are our forces. So I see we've got t cosine theta, and it's going up. So let's define the up direction as being the plus direction. So it goes in with the plus sign. And then we got mg, which is going down. So it goes in with a minus sign. And that's equal to mass times acceleration. But what is the acceleration in the y direction of an object that is only moving in the horizontal direction? Okay, this object is moving purely in a circle, horizontal circle. So there is no y acceleration. The y acceleration is 0. Okay, so then anything times 0 is 0, so bingo. All right, so now we have two equations. So you see the math is getting a little bit more complicated than it was the first time, but it's still very much doable. All right, so let me just clear a little bit of room here. Okay, so let's combine these equations together. Now, when we did this, a week or so ago, when we had the masses on the pulleys, you'll remember that when we had the two equations and two unknowns, we used the elimination method in order to combine the equations. Well, we can't do that this time because one of the variables that we're working with is theta. And you can see that that variable is inside of a trig function. And you can't do linear combination, or which is also called the elimination method. You can't use the elimination method if one of the variables you're dealing with is inside of a non-linear function, like a trig function or exponential or the others. So we're going to have to use the substitution method here. And that's okay. That's not that hard to do. All right, so tell you what, let's bring this guy on. Oops, I hate it when I forget that I'm still in erase mode here. Okay, so let's bring this guy over on the other side. And so what we're going to get is t cosine theta equals mg. So t then equals mg divided by the cosine of theta. All right, so wherever we see a t, we'll replace it with the thing that we know t is equal to. Right? That gives us, so mg divided by the cosine of theta times the sine of theta equals mv squared over r. And now we notice the mass cancels out. So it turns out we don't need to know what the mass is. It cancels out. That's nice. Can we simplify this any? If we've got sine theta on top and cosine theta on the bottom, you guys remember sine theta over cosine theta, that's the same thing as tangent theta. Okay, so then we got g times the tangent of theta equals v squared over r. So if I tell you what theta is, then I think we can solve this, but there's one very important catch. R. What is R? Now, some of you are going to say, well, isn't that the length of the string? To which I'm going to say, not in the real world. When we did the simplified problem a few minutes ago, problem number whatever it was out of the book, where we assumed that theta was basically 90 degrees, the radius of the circle that the object was moving in was basically the length of the string. But that's not going to be the case now, because now the object is hanging down a little bit. And so the radius of the circle is this r down here. The length of the string is L here. So r is not equal to the length of the string. But there is a good relationship between the two of them. The length of the string L, that's the hypotenuse of the triangle. And if we know theta, or if we want to know how it's related, hopefully you guys realize that R is just going to equal L times the sine of theta. Okay, so R over here is L times the sine of theta. Okay, so now we can finish this up. So if we want to know what V is, so if I were to tell you what theta is, and I were to ask you to calculate what is the velocity that makes that happen, well, we can solve that pretty easily. I'm going to leave it as R for right now. I'm going to multiply both sides by R, make that go away, recognizing that R is really L sine theta, right? So then I'm going to take the square root, and then I'm going to replace R with L sine theta. So V then is going to equal the square root of L times the sine of theta times G times the tangent of theta. That is the equation that if I tell you what theta is, then you can calculate what is the velocity that the thing needs to be moving at in order for that angle to be true. Okay, so let's put in some numbers. I think I said that I wanted it to be, yeah, I did. I said here it was 85 degrees. And the length of the string, let's just pick some number at random. Let's say that it's 1.5 meters. Okay, so let's put that in for there, put that in for there, that in for there. And we already know what G is 9.8. Okay, so do I need to actually do the calculations? I mean, hopefully you guys agree this is pretty straightforward, right? Okay. So if I tell you what theta is and ask you to calculate V, bingo, you got it. It's a little bit more complicated, I'll admit, but not horrendously so. What if I do it the other way around? What if instead of telling you what theta is and asking you to calculate V, what if I tell you what V is and ask you to calculate theta? Okay. Well, that's going to make the problem a lot more interesting. So tell you what, let me write, I'm going to open up a whiteboard. Before I do, I want to write down this equation. So we got the square root of L times the sine of theta times G times the tangent of theta equals V. Okay, so let me open up a whiteboard. So we have just calculated that when you have a mass on a string and length L and is moving in a circle like this of radius R, we've just shown that the square root of L sine theta times G times the tangent of theta equals V. And we found that if I tell you what theta is and ask you to calculate V, that's pretty straightforward. But if I tell you what V is and ask you to calculate theta, then the math gets a lot more interesting because we got a theta over here and we got a theta over there. How can we solve that? Well, some of you are in Math 3. And so hopefully those of you that are in Math 3, you know that there are some tricks that you can do. There are things called trig identities that you can do. And if you're really good at using trig identities, you could possibly solve this problem. But I also know that many of you are not in Math 3 honors right now. And so you're looking at this, you're saying, I have no idea how to solve this. Well, I'm going to teach you a method right now that sometimes the Ames math teachers get a little bit unhappy with me for teaching you this method, because what I'm going to teach you is, well, it could be considered cheating. I'm going to teach you how it is that you can solve any problem at all, no matter how complicated the math is, as long as you can get it down to one equation, one unknown. If you can get it down to one equation, one unknown, then you don't need to know all those trig identities and all the fancy things that you really should know. But there's a neat way to solve it. So let me show you how this works. Okay, so I'm going to take this equation and I want to solve it for theta. And so the way that ninth graders like to do it is take everything that's not theta and get it over on the other side. But in this case, that's not going to work because we've got one inside a sine and one inside of a tangent. So what I'm going to do is I'm going to rearrange my equation here to make it so that it equals 0. Okay, so that's easy. All I have to do is subtract a v from each side. And so what I'm going to get then is the square root of L times the sine of theta times g times the tangent of theta minus v equals 0. Now, what I'm going to do is I'm going to say, what if instead of making it equal 0, what if I were to make that into, say, y? And instead of calling this theta, if I were to call it x, what I've got is I've got y equals some complicated equation that's got an x in it here and it's got an x in it there. If only there was a software package or a website that could graph really complicated equations, what I could do is I could put this equation into that website, and then I would get a graph that, maybe looks like this, okay? And it's going to be a really messy graph. But remember, I want to know when does y equals 0. So all I have to do is put it into there and then look to see what is the x value that makes y equals 0. That will be the answer. Okay. So you guys know, of course, that there is, in fact, a wonderful website. Everybody's favorite website, certainly my favorite anyway, Desmos. All right, let's go here to Desmos, which I just happen to have open here, but let's get rid of that. Okay. So what I'm going to do is I'm going to take that equation. Now it is important, you have to rearrange the equation so that you get it in the form of, hang on a sec while I get my annotation here. You got it get it in the form of y equals something, okay? But what we really want is 0 equals that something, right? Okay, so what is the something? Well, let's open up the equation editor here. Okay, so we're going to say y equals the square root of L, which, what did we say L was? L was 1.3, right? Oh boy, I forgot. What did we say L was?
I think it was 1.5.
1.5, okay, thanks. 1.5, okay, times the sine of theta. Okay, so times the sine. And now Desmos is happier if we call it x rather than theta. So we'll do that, okay. Times g, which is 9.8, okay, times the tangent of theta. Except Desmos is happier if we call it x, so we'll call it x, okay. And then we want to do minus the velocity. All right, so I need to tell you a number for the velocity. So let me just pick a number out of the blue. Let's say that the velocity is 25 meters per second, okay? So if I say that the velocity is 25 meters per second, bingo. So what I have now is a graph of this. Now you might say, what do you mean graph? I don't see any graph. Well, let's try zooming out. Aha, look at this, okay? We get some complicated graph and we see that the answer there is some number pretty close to 90. And if we zoom in closer here, we can see it looks like it's about 88 point something. And if I click on the line, or if I click on the graph itself, so you can see it's 88.65. Okay, so what that tells me is that if I spin this ball so that the velocity of the ball is 25 meters per second and the length of the string is 1.5 meters, that ball is going to hang at an angle of 88 point what? I forgot already. 88.6. Oh, so let's just call it 88.6 there. Let's just call that 89. Okay. So if you round it off for 2 sig figs, 89 degrees. Okay. So you see that the physics that we just did is not really any different than the physics that we did for last night's homework. But the mathematics was definitely more complicated. So this is tonight's homework is going to give you guys some really good practice at solving more challenging problems. And even if you're not in the Math 3 Honors class, it is possible to solve the problems that you're going to see here. Okay. Now, let me give you one more example to work on that's very similar to what you're going to see in tonight's homework. And it's one that if we don't talk about it in advance, you might not know how to approach it. So let me open up a new whiteboard. Okay. Remember in your homework last night, one of the problems had to do with a car going around a curve, and you had to calculate what's the maximum speed that the car could travel at without sliding off the road. I think that was problem number 65, which we didn't talk about. You guys didn't ask about it. So I assume that means that you understood how to do it. But tell you what, just in case you're one of the people who didn't understand how to do problem number 65, let's do it right now. And then we'll make it more interesting for tonight's homework. But first, let's make sure we know how it worked last night. So if I look at a top view of what's happening, so imagine I'm in a helicopter up above looking down. Here's the road. Here's the car. The car is moving at some velocity v, and the track has some radius r. Now in problem number 65, let's see let me actually use the same numbers from problem 65. Okay, we said that the radius of the track was 80 meters. That doesn't look like an 80, but that's actually an 80. Let me try that again. So 80 meters. And we said that the coefficient of friction was 0.4. Yes, it was 4, 0.40. So we wanted to know what was the maximum velocity that you could travel at before the car goes sliding off the road. All right, so we know that there's a force that's keeping the car on the road, and that force is the force of gravity. I'm sorry, is the force of friction, force of friction. So if I do a free body diagram, there's my force of friction. Notice that it's always pointing toward the center of the road, or center of the circle. So I'm going to draw a rear view picture like I did a few minutes ago. I find that it's helpful if we imagine that we are in a car following behind the car that we're interested in. And so here's let me change it to a not so thick pen there. So here's the car that we're interested in. Here's the tires. Here's the road. All right, let's do a free body diagram. So we got, and I want my free body, I like my forces to be fat. Okay, so there's mg going down. There's the normal force going up. And then the car is turning to the left. So there's the force of friction. All right. Now, when you'd solved this problem last night, seeing as how nobody asked questions about it, I assume that you knew the way to do it. was we're going to say sigma F in the x direction equals the mass times the acceleration in the x direction. And in the x direction, there's only one force. That's the force of friction. And the acceleration in the x direction, if you're going around a circle at constant speed, your acceleration is v squared over r. Now, what is the defining equation for friction? It's mu times the normal force. What is the normal force if you're on a flat surface? It's mg. So mu times mg equals mv squared over r. And so when you did this problem last night, you recognize, well, hey, we don't even need to know the mass of the car. It cancels out. So if we multiply both sides by r and take the square root, then what we get is that the square root of r times mu times g equals the velocity. Okay, so that tells us what is the maximum speed that the car can have when it's going around the corner here without sliding off the road. So let's just go ahead and punch it out just so we have the numbers. So r was 80, so I'm going to take the square root of 80 times mu, which is 0.4, times g, which is 9.8. So when I do that, I get 17.8, which is too many sig figs. So 18 meters per second. That is the maximum speed that the car can have without sliding off the road. If it goes any faster than that, it's going to slide off. If it goes any slower than that, no harm. Okay, but if it goes any faster than that, it's going to go sliding off the road. Okay, so that was the problem that we did in last night's homework. How could we make this more interesting for tonight's homework? Well, you guys know that if you go to a high-speed racetrack, if you go to the Daytona Speedway or any other place that's a race that's designed for racers, what you'll find is that when they come to the curve, the curve on the road there the road is tilted. So this picture that I drew right here, it would look different. If you were in a race car on the Daytona Speedway and you were to draw a free body diagram of the car in front of you, well, the first thing you'd have to do is you'd have to recognize that the road is not level. The road is tilted like this. And so then the car is going to look like this. Here's the car, here's the tires. So when you do your free body diagram, you're going to have mg going down. And again, I like my forces to be fat arrows. So there's mg going down. There's the normal force going up. Okay. Now, if the car is going around the curve really, really fast, so fast that we're worried that maybe the car might skid off the road, well, what's keeping it from skidding off the road? Friction. And so if the curve is curving to the left, so the car wants to slide off to the right. So friction always opposes that. So the force of friction is going to look like that. So you see how this is a much more interesting problem than on last night. Okay, we have what's called a banked road now. Okay, now in tonight's homework problem, they are not going to ask you what is the maximum speed the car can have without sliding off the road. They could. That is a problem that you guys have the ability to solve. But it's a little bit easier if instead of asking the problem that way, let's change the problem a little bit. Let's assume that it's a snowy day in Daytona and there's ice on the road. And so we want to know what is the speed that you could go around this curve at and not slide either up or down. Because hopefully you guys realize that if there is no friction, because if there's perfectly frictionless ice on the road, then you've got a problem. When you go around the curve, you got to be careful not to go too fast, but you also have to be careful not to go too slow. Because if you go too slow, you're going to end up sliding down the hill. If you go fast, you're going to go sliding up the hill. So what they're going to say is they're in tonight's homework problems, they're going to say, let's tell you a velocity. Let's say that the velocity equals some number that they give you, okay? And then they're going to ask you, what is the angle of the bank, so that if you go at this speed, then you will neither slide up the hill or down the hill, assuming that there's no friction. Okay. So I don't want to say too much more, because if I do any more, then heck, I'm going to have solved the problem for you. And I don't want to solve the problem for you. Okay. But you can see how this is a problem that's very similar to last night's homework, but it's got an interesting twist that makes it a little bit more challenging, a little bit more interesting. Okay, so I think you're ready to do tonight's homework, but there is one thing I do need to warn you about. There is a mistake in the book that if you don't, if you're not aware of it, you're going to really scratch your head for a long time saying, what's the deal? Problem number 80 in the homework tonight. And by the way, you've only got 3 problems because I recognize that these problems are a little bit more challenging. It's going to take you a little bit of time. So I figured, okay, I'll just give you 3 problems. That'll be enough to keep you busy. Okay, so problem number 80, they show you a picture that looks like this. They say that a person is swinging a ball on the end of a string, and they're saying that the angle is 14 degrees. But does anybody notice anything wrong with this picture? Well, let me go ahead and just tell you what's wrong with this picture.
It's tilted up.
Yes, it's tilted up, exactly. That's impossible. There's no way that that can be, right? There's no way that the ball can be higher than the hand. That's just impossible. So I think what happened was when they made the book, the artist who do the drawing was apparently not a physicist, and the authors who wrote the book, they didn't look closely enough. Okay, there's no way the ball can be higher than the hand. So this is the real picture right here. Okay, so when you're doing problem number 80, this is the person's hand right here. And the ball is below the hand, which is the only way it could be. And what they're saying is that this angle here is 14 degrees. Okay, so they're telling you what the velocity is, and they're asking you, or I'm sorry, they're telling you what the angle is, and they're asking you to find what is the velocity of the ball. Hopefully you guys remember when we did this a few minutes ago, they are giving it to you the easy way. If they tell you the angle and ask you to calculate the velocity, that's the easy way. The way that's more fun would be if they told you what the velocity was and asked you to calculate the angle. That's much more challenging. But you guys now know how to do it, so you could do it either way. All right, so I think you guys are now ready. If you would like to just go ahead and type bye into the chat box and sign off, I'm okay with that. If you have any questions you want to discuss, I'm here for you. If you'd like me to turn off the recording so you can ask questions that are potentially embarrassing and you don't want them to be recorded, then that makes sense. So here what I'll do is I'll turn off the recording.